This is a review of the Earth's atmosphere. The Earth's atmosphere is in several distinct layers. The most important of these is the troposphere. This is the lowest level, closest to the ground, and contains all of the Earth's weather, 99% of the world's water vapor, and all the living organisms. Just above that layer is the stratosphere. The stratosphere is much colder and thinner, and it's critically important because it's where the ozone layer is, which we'll do in another presentation. The ozone layer, though, is the layer that blocks 98% of the world's UV radiation, allowing life to exist. There's a super thin layer above that that's very cold called the mesosphere. But then there's another critically important layer near the top of the atmosphere at the edge of space called the ionosphere. This is a layer that protects the Earth from cosmic radiation, blocking X-rays, gamma rays, and particles from the sun. The current composition of the Earth's atmosphere is about 78% nitrogen, 21% oxygen, and just under 1% argon. Then there is a series of trace gases, and the most important of those is carbon dioxide. Carbon dioxide is in small quantities, but is critically important, of course, because it's used in photosynthesis and is a powerful greenhouse gas. Then you have water vapor, which can vary quite a bit in its percentage depending on the humidity. Over the whole atmosphere, it represents about 0.4% of the atmosphere, but near the surface it can range from about 1 to 4%. Now let's talk about the kind of energy that comes into the Earth's atmosphere and how that affects the atmosphere. Now, this is a review over stuff you've learned before, but of course, energy can arrive to Earth in the form of electromagnetic radiation, including radio waves, very long wavelengths with low energy, microwaves, infrared, which we mostly detect in the form of heat, the visible part of the spectrum, which we can see, ultraviolet radiation, which is high energy radiation that's absorbed by the ozone layer, extremely high energy radiation like X-rays, which can pass through most things except for metals, and then the most dangerous of all of them, which is the gamma rays. Now, infrared radiation is really important because it's the source of energy that tends to heat things up. And the warmer things are, the more of this infrared radiation they're going to release. One of the things that keeps the planet warm is something known as the greenhouse effect. As things heat up inside of a greenhouse, they're going to absorb that visible spectrum radiation and then re-radiate that energy in the form of infrared. Now, glass allows visible light to pass through it, but it blocks infrared radiation and reflects it back inside the greenhouse. So visible light gets converted to infrared, heating up the greenhouse. This is one of the reasons why your car gets hot when it's sunny, because your car is basically acting on the greenhouse effect. Solar radiation enters through the window in the form of visible light. It's absorbed by the things in your car, like your seats, and then it's re-radiating that energy in the form of infrared, except that glass doesn't let infrared through, so that infrared stays inside the car, making it hotter and hotter. That's why it's so important that you not leave animals or babies inside of a car, because they can heat up dramatically. Even a 70-degree day can result the inside of the car being over 100. Here's a question for you. Have you ever gotten a sunburn while driving your car? I mean, your arm is sitting there, the sun's shining through the glass and it's hitting your arm. But do you ever get a sunburn? Well, as it turns out, in addition to not allowing infrared through, glass also blocks UV radiation. So the visible light goes through, but the UV is blocked. That's why sometimes you'll get something called a trucker's tan, because you've got one window down and you've got your arm sticking out and the rest of your body's not getting exposed to the UV radiation. Okay, so that's glass. As it turns out, there's a few gases in the Earth's atmosphere that also act like glass in terms of what we call greenhouse gases. These are gases that allow visible light to pass through, but block infrared radiation from being reflected back. So if you look at this diagram, you'll see that a lot of the visible light hits the Earth and is actually reflected back into space. This isn't the case with like clouds or ice or light surfaces. The darker surfaces that absorb that visible light then re-radiate that energy back out towards space in the form of infrared. But some of these greenhouse gases will capture some of that infrared and reflect it back toward the Earth, causing the Earth to warm up. The most common greenhouse gas on the planet is carbon dioxide. In addition, methane, water vapor, nitric oxides, and CFCs, which we talk about in the ozone presentation as well, are all powerful greenhouse gases. As it turns out, oxygen and nitrogen are not strong greenhouse gases. So let's talk about what the Earth would be like if it didn't have an atmosphere. So we have an example of this nearby, the moon. Our moon gets the same amount of sunlight that the Earth does because it's the same distance from the sun. But it doesn't have an atmosphere that can absorb solar radiation. So if you're standing on the moon at the equator, the temperatures are going to fluctuate wildly because there's no atmosphere that could capture that heat. If you were standing in the darkness, in the shadow of a rock or on the dark side of the moon, you'd be sitting in temperatures that are 170 below zero. However, as soon as you get hit by sunlight, you're going to heat up dramatically to about 125 degrees Celsius. That's why when astronauts were walking on the moon, they had to have spacesuits that had both heaters and air conditioners inside that could regulate those dramatic changes in temperature, avoiding the astronauts avoiding freezing and boiling. By contrast, if you look at the Earth's equator, the temperatures don't range very much. They basically go from about 23 degrees at night to about 33 degrees Celsius in the day. And that's because the solar radiation is being absorbed by the atmosphere and spread out across the atmosphere. And then when it goes to nighttime, that atmosphere is able to hold on to a lot of that heat through the night without radiating it back into space. So the Earth is livable because of the presence of greenhouse gases. It's estimated that the Earth is about 59 degrees Fahrenheit warmer due to the greenhouse effect than it were if we had no carbon dioxide or methane in the atmosphere. 59 degrees Fahrenheit is the difference between being in a tropical rainforest and being in a frozen tundra. If you think about it, if it was 80 degrees Fahrenheit at the equator, that's a pretty warm day. Take 60 degrees off of that, and it's only 20 degrees, you're below freezing and you have ice. However, you can have too much of a good thing. Look at Venus, our neighbor, as same size as Earth, similar atmospheric and geological conditions, except its atmosphere is 96% carbon dioxide. So 96% of it is this powerful greenhouse gas instead of non-greenhouse gases like nitrogen and oxygen. In addition, Venus's atmosphere is 90 times thicker than Earth's. So this results in an extreme greenhouse effect where virtually none of the sunlight that enters Venus is able to escape. Thus, it has an average surface temperature of 872 degrees Fahrenheit. Okay, so let's talk about what happens to this sun's energy when it gets to Earth. The term that refers to what happens to this energy and how much of it's absorbed and how much of it's reflected is called insolation. So if you were to do 100% of the solar radiation entering the Earth's atmosphere, what you'd see on the diagram to the left is that 51% of the solar radiation that arrives to Earth is absorbed by the surface of the Earth. So it's absorbed by water, by rocks, by trees. About 3% is absorbed by clouds, and about 16% of it's absorbed by gases in the atmosphere itself, the ozone, water vapor, dust, things like that. About 30% of the of the radiation entering the Earth's atmosphere then just gets reflected back into space. About 20% of it just reflects off the cloud tops and goes right back to space. And about 4% of it is reflected off the surface. So 70% of the solar radiation arriving from the sun is absorbed by the Earth and its atmosphere and its oceans. Now, as things warm up, they're going to re-radiate that energy back into space in the form of infrared. Now, you all know that the equator is much warmer than the poles. The reason for that has to do with the angle at which the solar radiation hits. If you look at this diagram, you're going to see that the solar radiation hits the Earth's equator straight on and has, if you look at these two arrows, the band or the width at which that radiation is hitting is concentrated in a zone of just 1,000 kilometers wide. Versus, if you look at the pole, it's kind of spread out at an angle over 2,000 kilometers. So twice as much solar radiation hits the equator than does the poles, resulting in a much warmer temperature at the equator than the poles. Okay, so I mentioned that the Earth's composition are these gases that you see here, and 78% is nitrogen and 21% is oxygen, and neither of those is a greenhouse gas. So that 60 degrees of temperature that between freezing and being warm has to do with this tiny, tiny percentage, 0.038% carbon dioxide, and even tinier quantities of methane. But it wasn't always this way. Our Earth's atmosphere hasn't been this way for most of its history, and actually. Our modern atmosphere came about as we got into about 600 million years ago. Now remember, the Earth is 4.5 billion years old, so 600 million years ago really wasn't that long ago in the history of the Earth. But about 600 million years ago, plant life really started to spread across the surface of the Earth. And these organisms became abundant enough that they were absorbing all this carbon dioxide out of the atmosphere and releasing oxygen into the atmosphere. So the Earth started with much more carbon dioxide and therefore started much warmer, but it began to drop dramatically as forests began to cover the surface of the Earth. Because CO2 levels are found at very small levels, we typically refer to them in parts per million instead of percentages. So if you think about 1% representing 1 out of 100, then 0.1% would be 1 part per thousand, and 0.00001% would be 1 part per million. In the year 1750, when we began measuring CO2 levels in our atmosphere, we measured it at 0.028%, or 280 parts per million. In fact, we now know through ice cores and other data that the Earth's atmosphere has not been above 280 parts per million for the last 800,000 years. However, if you look at CO2 levels today, we're measuring it at 400 parts per million. And that's because as we dig up these fossil fuels and we burn them, we're releasing that CO2 back into the atmosphere that was captured by plants millions of years ago, and we're adding carbon into the atmosphere, and we've raised CO2 levels since the beginning of the Industrial Revolution from 400 parts per million from 280 parts per million to 400 parts per million. So let's go back again to about 500 million years ago. About 500 million years ago, it was over 6,000 parts per million of carbon dioxide in the atmosphere. That was trapping a lot of solar radiation, and so the entire Earth's surface was warm and wet, and we had these tropical swamps and forests all across the world. There were forests in Antarctica. There were forests all the way to the North Pole. There was no ice on planet Earth at that time because the Earth was so warm. As we reached about 200 million years ago, CO2 levels had dropped in half to just 3,000 parts per million. Where did those 3,000 parts per million go? Where did all that CO2 go? As plants absorb that carbon and put it up into their bodies, and then those plants began to die, much of that carbon was buried under the ground. This was a time where our fossil fuels were being formed. In fact, this whole period is known as the Carboniferous period because it's the time when all this carbon was being pulled out of the atmosphere and trapped underground. So this takes us to the carbon cycle. CO2 levels dropped from 6,000 parts per million down to a modern 300 parts per million as this carbon was being pulled out through photosynthesis. These dead and decaying organisms were buried underground, and that carbon was trapped underground in the form of fossil fuels: coal, natural gas, oil. Now, of course, most of it is being recycled in the normal carbon cycle. Plants die, animals eat those plants, bacteria break those plants down, and that carbon's released back into the atmosphere through respiration. But even if a tiny percentage of that carbon ends up being trapped underground, for millions of years, that little tiny amount can add up to a lot, and much of the carbon dioxide was pulled out of the atmosphere. So when we look at this land 500 million years ago, 300 million years ago, the Earth was so warm that there was no ice on the planet. Tropical rainforests covered almost the entire surface. And then it was buried underground. And this carbon was locked underground for millions of years, reducing the CO2 level in the atmosphere to something that's more similar to what we see today. And we can see where that carbon went. All you need to do is go up to Utah and see the bands of carbon in the form of coal. When you see coal, whether it be in West Virginia or Utah or Wyoming, coal was formed by terrestrial vegetation, ancient rainforests that were where the plants, when they died, were buried by mud and then they stayed underground, eventually compressing into coal. Petroleum or oil is found in these semi-aquatic or aquatic environments where algae and plankton settle down to the bottom of lakes in the ocean and were then buried in sediments. And natural gas comes out of both coal deposits and oil deposits. And in fact, natural gas is produced today by methanogenic bacteria. These are bacteria that live without the presence of oxygen, so they can't do respiration and produce CO2 like normal respiration. And as they break down that organic material in bogs and swamps, even in our landfills where we're taking our garbage, our food waste, and then piling it up, without the presence of oxygen, their byproduct becomes methane, which is the number one component. About 90% of natural gas is methane.